A cosmic abyss swallows even light, crushing matter into an unknowable point. Yet this terrifying reality might be a profound illusion. What if a black hole is not a final grave, but a gateway? We will explore the radical science suggesting these gravitational monsters could be tunnels to other dimensions. You will discover a new way to see the universe, learning how the very fabric of space and time might be woven with hidden passageways. We will confront the mysteries of what lies beyond the event horizon and how a journey through could rewrite the laws of physics. What forgotten corner of reality would you dare to explore? That one-way membrane, the event horizon, is not a solid wall but a silent threshold. Once crossed, every possible path leads inward toward the mysterious heart of the darkness, the singularity. This is the point where matter is crushed into infinite density, a place where the very rules of space and time as we know them cease to function. It is the ultimate unknown. But what if this breakdown of physics is not an end, but a transformation? The brilliant physicist Stephen Hawking proposed a radical idea that the universe might have no boundary, no true edge. This hints that a singularity could be less of a final stop and more of a cosmic crossroads, a transition into a different state of reality. This is where the gateway concept truly takes form, rooted in the predictions of Einstein's theory of general relativity. The mathematics suggest that the intense gravitational warping at a black hole's core could twist the fabric of spacetime into a tunnel, a theoretical passage known as an Einstein-Rosen bridge, or more commonly, a wormhole. Think of spacetime not as a flat sheet, but as a dynamic, malleable substance. A black hole's immense gravity could pinch this fabric, creating a bridge that connects two distant points, or perhaps two entirely different universes. For a traveler, the journey would be perilous, yet some calculations for very large, rotating black holes suggest you might just survive the passage. Instead of being shredded by tidal forces, you could theoretically pass through the wormhole's throat and emerge elsewhere. This is a profound shift in perspective. Black holes are no longer just cosmic trash compactors, but potential conduits to realms beyond our imagination. This incredible possibility forces us to ask, what kind of mathematics could possibly chart a course through such a chaotic passage? The universe might be folded like a piece of paper. Picture two dots on opposite edges of that sheet, impossibly far apart by any normal measure. Now fold the paper so the dots touch. That is the essence of a wormhole, a tunnel creating a cosmic shortcut through the unseen dimensions of space-time. This is not science fiction, but a serious mathematical prediction. In 1935, Albert Einstein and his colleague Nathan Rosen uncovered a profound possibility within the equations of general relativity. They found that the mathematical description of a black hole could be extended, connecting to another solution that looked like a white hole, a theoretical region where matter and energy can only escape. This connection formed a bridge, a structure we now call an Einstein-Rosen bridge. As the renowned physicist Kip Thorne noted, wormholes are a valid prediction of Einstein's theory of gravity. This gives the gateway concept a firm mathematical foundation. The bridge is formed by linking the space-time curvature of two black holes, creating a throat, a passageway that joins two separate regions of the universe, or perhaps two separate universes altogether. But there is a catch, a reason we have not found such a tunnel. The equations show this bridge is violently unstable. The moment it forms, the immense gravity would snap the throat shut, collapsing the passage in a fraction of a second. Anything attempting to cross would be crushed. For a wormhole to be traversable, to remain open long enough for a traveler to pass through, it would need a form of cosmic scaffolding. This is where the concept of exotic matter comes in. This is not merely strange matter, but a substance with a truly bizarre property, negative energy density. Think of it as a kind of anti-gravity material, something that pushes spacetime outward, propping the wormhole's throat open against the relentless force of gravity that wants to crush it. This exotic matter is the key ingredient in theoretical models for stable wormholes, the kind that could enable interstellar travel or even journeys through time, as dramatized in films like Interstellar. The very fact that our best theory of gravity not only allows for such structures but demands we consider what could stabilize them, pulls our search in a new direction. It forces us to look beyond the vast scales of relativity and into the bizarre, probabilistic world of the very small. The rules governing the very small are fundamentally at odds with the laws of gravity. While relativity paints a picture of smooth spacetime and predictable curves, the quantum world is a realm of uncertainty and probability. This clash of titans comes to a head at the edge of a black hole, creating one of the most profound puzzles in modern physics, the information paradox. Stephen Hawking realized that black holes are not truly black. Due to quantum effects near the event horizon, they slowly leak radiation and evaporate over immense timescales. But this creates a terrible problem. In quantum mechanics, information is never truly lost. Every detail about a particle, its spin, its charge, its identity must be preserved. If a book falls into a black hole, the information contained in its pages should, in principle, be recoverable. Yet if the black hole evaporates into a faint haze of random radiation, where did that intricate information go? It seems to be erased from our universe, violating a core quantum law. Physicist Leonard Susskind fiercely debated this with Hawking, arguing that the horizon is not a special place where physics breaks. He insisted information must be preserved, just transformed. The resolution to this paradox might be the very key that unlocks the gateway. The leading idea comes from the holographic principle, a concept emerging from string theory. It proposes a staggering notion. All the information about everything that falls into a black hole, every star, every planet, every astronaut, is not crushed into the singularity. Instead, it is perfectly encoded like a cosmic blueprint on the two-dimensional surface of the event horizon. Think of it like a hologram. A normal hologram is a flat, two-dimensional surface that creates a perfect three-dimensional image when you shine light through it. In a similar, far more profound way, the black hole's surface could hold all the data needed to reconstruct the three-dimensional objects that fell inside. This is not just a storage system, it suggests a processing mechanism. If information is not destroyed but translated onto a boundary, then what happens to it? Some theories propose that as the black hole evaporates, this encoded information is transmitted, perhaps leaking out with the Hawking radiation. Other, more radical ideas suggest it could be transferred entirely, projected into a new region of spacetime. The black hole would then act less like a shredder and more like a scanner, taking the information of what falls in and printing it out somewhere else, in a baby universe branching off from our own, or another part of a vast multiverse. This transforms the black hole from a cosmic dead end into a complex transformer of reality. The act of falling in could be a process of being deconstructed into fundamental information here, only to be faithfully reconstructed there. Resolving the information paradox does not just save quantum mechanics, it paints black holes as dynamic processes, potentially facilitating a journey of information across the fabric of reality itself. But for a physical object, not just data, to make that journey, the gateway must be held open against the will of the universe. That exotic matter, the cosmic scaffolding, is the most critical missing ingredient. It is not merely strange, it is fundamentally bizarre, a substance with negative energy density. Think of gravity as an attraction that pulls everything inward. Normal matter, the stuff that makes up our world, has positive energy and creates this attractive gravity, but exotic matter would do the opposite. It would generate a repulsive gravity, pushing spacetime outward. This bizarre push is exactly what you would need to prop open the throat of a wormhole, fighting against the natural tendency of gravity to slam it shut in an instant. The concept appears in other radical theories, like physicist Miguel Alcubierre's warp drive. His idea uses a shell of negative energy to contract spacetime in front of a ship and expand it behind it, effectively allowing the ship to ride a wave of distorted space without breaking the speed of light. The same principle applies here. To create a stable, traversable gateway, you would need to line the tunnel with this exotic material, creating a force that counteracts the crushing weight of the cosmos. We even have a tiny, laboratory-scale hint that such negative energy is possible. It is called the Casimir effect. When you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, the empty space between them actually develops a negative energy density. The quantum fluctuations that normally exist everywhere are restricted between the plates, but not outside, creating a subtle pressure that pushes the plates together. This is a verified quantum phenomenon. The problem is one of scale. The negative energy produced in the Casimir effect is incredibly faint, a mere whisper. To hold open a wormhole large enough for even a single atom to pass through, you would need a deafening roar of negative energy, a concentration beyond our current comprehension. This immense challenge forces a profound question. If black holes are natural gateways, then nature must have found a way. Perhaps certain types of black holes, like the supermassive, gently rotating ones at the centers of galaxies, naturally generate or attract the conditions needed for stability. Their immense size and specific properties might create a form of scaffolding we have not yet learned to detect, turning a mathematical possibility into a physical reality. The search for this exotic substance bridges the gap between a beautiful equation and a functioning gateway, pulling our gaze from the abstract to the astronomical, to the specific objects that might hold the key. The true nature of a black hole is shaped by its spin. A rotating black hole, described by the Kerr metric, is a fundamentally different beast from its static cousins. Discovered by mathematician Roy Kerr in 1963, his solution to Einstein's equations revealed a structure far more complex and dynamic. At its heart lies not a point of infinite density, but a ring singularity, a loop where the known laws of physics break down. This simple change from a point to a ring has staggering implications for the gateway hypothesis. Surrounding the event horizon of such a spinning monster is a region called the ergosphere, a cosmic whirlpool where space and time are dragged around at incredible speeds. You cannot stand still here, no matter how powerful your engines. The fabric of spacetime itself is flowing like a relentless river, pulling everything with it. This furious motion is not just a spectacle, it is a source of immense power. Physicist Roger Penrose theorized a way to tap this energy, a mechanism now known as the Penrose process. An object could enter the ergosphere, split in two, with one piece falling into the black hole and the other flung out with more energy than it entered with. The black hole itself loses a tiny bit of its rotational energy in the exchange. This proves that the area around a Kerr black hole is a maelstrom of usable force. But the most profound possibility lies within the ring singularity itself. Because it is a ring, not a point, some mathematical solutions suggest that an object could, in theory, pass through its center without being crushed into oblivion. It would not hit an infinite density wall, but could instead find a pathway to another region of spacetime. In a maximally extended Kerr black hole, the equations reveal a theoretical labyrinth with connections to other universes woven into the very fabric of its structure. This makes rotating black holes the most promising candidates for natural, stable wormholes. The rotational energy seems to smooth out the violent instabilities, offering a potentially navigable corridor through the cosmos. So the ultimate fate of a traveler might not be destruction, but translation, carried by the whirlpool of spinning space into a realm beyond our own. Spaghettification is a terrifyingly accurate name for the process. As you fall towards a black hole, the difference in gravity between your head and your feet becomes overwhelming. If you were descending feet first, the pull on your feet would be vastly stronger than the pull on your head. You would be stretched, elongated into a long, thin stream of atoms, much like a piece of pasta. This is the brutal reality of tidal forces, a direct consequence of gravity's strength depending on distance. The force increases with the inverse square of your proximity, so getting close to a massive object means the part of you that is closer gets pulled immensely harder than the part farther away. We have even observed this cosmic violence on a stellar scale. Astronomers have watched as stars wander too close to supermassive black holes, only to be shredded into luminous streams of gas, a process fittingly called a tidal disruption event. For a stellar mass black hole, this spaghettification would happen long before you ever reach the event horizon. You would be torn apart by the extreme gravity gradient. But scale changes everything. Consider the supermassive black hole at the heart of our own Milky Way, Sagittarius, a star. Its event horizon is so vast, its gravitational field so spread out, that the tidal forces at the point of no return are surprisingly gentle. You could cross the threshold intact. The sky may call to us, as Carl Sagan said, but the nature of that journey depends entirely on the size of the doorway. This distinction is everything. It suggests that if black holes are gateways, only the largest, most massive ones could ever serve as safe passageways. You would need a colossal entrance to survive the approach, a doorway so wide that the lethal stretching forces are minimized at the critical moment of crossing. So the very physics that makes black holes dangerous also points to the specific type that might be useful, turning a cosmic monster into a potential corridor. But surviving the threshold is only the first challenge. Once you are inside, what reality would you encounter? A white hole presents the perfect cosmic mirror to a black hole. While a black hole is a one-way street where matter and energy can only fall in, a white hole is a one-way street in the opposite direction. Nothing can enter a white hole, it can only pour out. Imagine a cosmic fountain, endlessly spewing a torrent of light and matter into space, a geyser with a source that remains forever hidden and inaccessible. This is not merely a fanciful idea, but a direct mathematical consequence of extending the equations of general relativity. If you take the solution for a black hole and reverse the direction of time, you arrive at the description of a white hole. It is a perfectly symmetrical counterpart, a potential exit for the gateway system. The theoretical physicist Sean Carroll has even suggested that the most dramatic white hole of all could have been the Big Bang itself, a singular moment where our entire universe erupted from a single point of infinite energy and density. This idea transforms the gateway concept into a complete loop. A wormhole could connect a black hole in our universe to a white hole in another realm, forming a cosmic tunnel where anything that falls into the black hole is eventually expelled from the white hole. You would not be falling into a crushing singularity, but traveling through a bridge and emerging into a new reality. Yet this elegant symmetry faces a harsh cosmic reality. Theoretical models suggest white holes are profoundly unstable. The moment they begin spewing out matter, the intense energy and radiation would likely cause them to collapse almost instantly, perhaps sealing the gateway shut in a flash. This could explain why we have never observed one. They may blink in and out of existence too quickly for our telescopes to catch. Some cosmologists propose a fascinating alternative, that a white hole does not appear within our universe at all, but instead manifests as an entirely new universe budding off from our own. In this view, every black hole in our cosmos could be the seed for a new reality, a baby universe with its own laws of physics, forever separate from its parent. This idea enriches the gateway hypothesis with a profound destination. It pushes us to ask a staggering question. If black holes can birth new universes, could our own vast cosmos be the result of such an event? Are we living inside the aftermath of a white hole explosion from a parent universe? This possibility weaves the story of black holes directly into the fabric of the multiverse, suggesting that these dark giants are not endpoints but creators, the engines of cosmic reproduction across an infinite tapestry of realities. Our universe might not be the only one. It could be a single bubble adrift in a vast cosmic foam, a multiverse of countless other universes, each with its own unique set of physical laws. Some might have stronger gravity, others might have no stars at all. This grand vision of the multiverse provides the ultimate stage for black holes as gateways, suggesting they might not just connect distant points in our universe, but could be tunnels to these entirely different cosmic realms. Think of our entire reality as a membrane, a three-dimensional slice physicists call a brane, existing within a higher dimensional space known as the bulk. This is a core idea from string theory, often called the brane world scenario. As physicist Brian Greene has suggested, the multiverse is a natural extension of our current understanding of cosmology and particle physics. In this picture, a black hole could be a profound puncture in our brain, a place where the fabric of our universe is so warped that it taps into the higher dimensional bulk, potentially creating a bridge to another brane, another universe altogether. The singularity inside a black hole might not be a dead end, but the very point of connection, a tangled knot where the laws of our reality fray and interweave with those of another. This transition could be transformative. The constants that govern our world, the speed of light, the strength of nuclear forces, might be completely different on the other side. You would not just be traveling through space, but through the very rules of existence. Consider the ekpyrotic universe model, which proposes that our Big Bang was not a singular creation from nothing, but the result of a colossal collision between two such branes moving through the higher dimensional bulk. This is a staggering idea. A black hole in this context could be a more focused, stable version of such a collision point, a permanent gateway born from the same cosmic mechanics that might have birthed our entire cosmos. This elevates the gateway hypothesis to a truly cosmic scale. Black holes are no longer mere doors for potential travelers. They become creators, the very mechanisms by which new universes are seeded within an infinite multiverse. The darkness we see might not be an end, but a womb for new realities. The fundamental nature of reality may be woven from music. The universe's most basic ingredients are not tiny dots of matter, but unimaginably small, vibrating loops of energy called strings. Different vibrational patterns, like distinct musical notes played on a single violin string, give rise to every particle and force we know. A specific vibration creates an electron, another creates a photon of light. As physicist Michio Kaku has elegantly stated, physics is the harmony on these strings and chemistry is the melodies we play on them. This beautiful idea, string theory, demands a grander stage for its performance. To make the mathematical symphony work, the universe must have more than the three spatial dimensions of length, width, and height that we experience. There could be 6 or 7 extra spatial dimensions, but they are curled up into a space so infinitesimally tiny, 1,000,000 trillion times smaller than an atom, that they remain completely hidden from our perception. Imagine a single point in the room around you. At that point, and at every other point, exists a tightly wound, microscopic knot of extra-dimensional space, a hidden landscape existing all around us that we simply cannot see. This is where black holes re-enter the story with revolutionary force. A black hole's immense gravity could be so powerful that it unravels these tiny, hidden dimensions. It could stretch and expand them, transforming a microscopic loop into a macroscopic passageway. In this view, a black hole is not just a tear in the fabric of space-time, but a puncture into these higher dimensional realms. The gateway concept finds a new, more robust home here. Some string theory models describe black holes not as having a crushing singularity at their center, but as being fuzzy balls or fuzzballs. A fuzzball is a dense, tangled ball of strings and the fundamental branes that give them structure. There is no point of infinite density, no place where the laws of physics break down. Instead, the entire interior is a chaotic, vibrating ball of stringy energy that extends all the way to the event horizon. The fuzzball's surface holds the information of everything that fell in, just like the holographic principle suggests, but its interior is a complex, higher-dimensional object. This provides a stunning resolution to the singularity problem. You would not hit a dead end. You would transition into this tangled, stringy interior, which, due to its connection to the extra dimensions, could theoretically serve as a bridge to another part of the cosmos or a different universe altogether. The gateway is not a tunnel through nothing, but a pathway through the vibrant, higher-dimensional substrate from which our own reality is built. This theoretical framework, which finally unites gravity with quantum mechanics, suggests that black holes are not tombs but dynamic transformers, translating matter and energy from our three-dimensional world into the richer, multi-dimensional landscape that is the true foundation of everything. The swirling chaos around a black hole is not just a spectacle, it is a cosmic laboratory, a source of real data where we can test our wildest theories. We see this in the brilliant, churning disk of superheated gas and dust, the accretion disk which spirals into the abyss at nearly the speed of light. This material glows with immense energy, painting a fiery outline around the darkness. The Event Horizon Telescope achieved the impossible, giving us our first direct image of such a shadow, the black hole at the heart of galaxy M87. It showed a brilliant ring of light circling a deep, dark void, a perfect match for Einstein's predictions. Astronomer Heino Falk, who helped lead this monumental project, expressed the awe of the moment, saying, "We have seen what we thought was unseeable." This shadow is the Event Horizon silhouette, the gateway's doorstep, but the real clues to its nature may lie in the anomalies, the behaviors that push beyond our standard models. Consider the relativistic jets, colossal beams of particles that scream away from some black holes at nearly the speed of light. Where does this incredible energy and focused material come from? One tantalizing possibility is that these jets are not just powered by the black hole's spin, but are the exhaust, the output of a gateway. Matter falling into the black hole on one side could be funneled through a wormhole throat and violently expelled from a connected white hole elsewhere. We can also search for more subtle signatures. A wormhole's gravitational lensing effect, the way it bends light from stars behind it, would be subtly different from that of a pure black hole. It might create a distinctive pattern, a fingerprint in the starlight, And then there is Hawking radiation itself. As a black hole evaporates over eons, this faint glow could carry more than just heat. If the black hole is a gateway processing information, the radiation might be imprinted with a scrambled code, a faint echo of what lies on the other side. Finding such a pattern would be like discovering a cosmic message in a bottle. These are the frontiers of observation, where we move from pure speculation to testable science. We are learning to read the universe's signals, searching for the cracks in reality that might reveal a passage through. But if such a passage exists, what would it truly mean to step through? The journey itself presents dangers beyond our current understanding. The journey through a black hole gateway would be the ultimate test of survival. We have already seen how tidal forces could stretch a traveler into a stream of atoms, but that is only the first and most predictable danger. The interior of a theoretical wormhole is a seething quantum environment, wildly unstable. The tunnel itself could collapse at any moment, crushing anything inside to nothingness. This quantum instability means your passage would be a desperate race against the spontaneous decay of spacetime, a gamble where the odds are almost certainly not in your favor. But even if you somehow survived that, you might face a threat far stranger than being crushed. The warped geometry inside a rotating black hole could create what physicists call closed time-like curves. These are pathways through spacetime that loop back on themselves, allowing for travel into your own past. Imagine stepping out of the gateway not just on the other side of the galaxy, but in a different century long before you were born. This is not mere science fiction, but a genuine mathematical possibility within general relativity. Such a journey would shatter the principle of causality, the fundamental rule that cause must always come before effect. You could, in theory, create a paradox like preventing your own birth. To resolve this logical nightmare, the physicist Igor Novikov proposed a compelling idea, the self-consistency principle. He argued that the laws of physics would simply not allow a paradox to happen. Any attempt to change the past would inevitably fail, as your actions would have already been a part of the timeline you remember. The universe would act as its own police officer of chronology, enforcing a consistent history through subtle, unavoidable forces. You might find your weapon jamming at the critical moment, or a sudden distraction pulling your attention away, ensuring events unfold exactly as they always have. Beyond these mind-bending temporal dangers, the environment itself would be lethal. You could be bombarded by intense radiation from the accretion disk or from the Hawking radiation glow near the event horizon. And then there is the singularity, or whatever lies in its place. Crossing that threshold would plunge you into a realm of quantum gravity, where the known laws of physics completely break down. Matter might be torn apart into its most fundamental components, not just atoms, but even the very threads of string that make them up. The gateway could lead to a universe with different physical constants, a place where the air is poison or the very atoms cannot form. These are not just engineering challenges, they are fundamental barriers rooted in our incomplete understanding of the cosmos. The sheer scale of these dangers suggests that traversing a black hole may forever remain a theoretical possibility, a journey too perilous for any physical being to undertake. It forces us to confront a humbling truth that some doors in the universe might be meant for opening, while others are meant only for wandering about from a safe and respectful distance. These gateways force us to question the very nature of what is real. Our reality is built upon a set of stable physical constants, a delicate balance that allows for atoms, planets, and life itself. But if a black hole leads to a cosmos where gravity is 1,000 times stronger, or where time flows backward, then our universe is not the only possible reality. It is merely one version, one setting in a vast cosmic library of existence. the philosopher Nick Bostrom asked if we might be living in a simulation. If black holes are gateways, they could connect to realities that are, in fact, elaborate simulations running on some unfathomable computer in a base universe. This does not make our experiences less real, but it profoundly expands the canvas of what reality might be. Stepping through such a gateway would be more than a journey, it would be a transformation. If you emerged in a universe where the speed of thought is the fundamental constant, not the speed of light, would you still be you? Your memories, your sense of self, are all tied to the electrochemical processes of a brain built for this specific reality. In a new cosmos, those very processes might not even function. Your identity, the continuous thread of your consciousness, could be severed or rewritten by the new laws of physics. This leads to a haunting question about the self. If your body is deconstructed into information as you cross the event horizon, and that information is used to perfectly reassemble you on the other side, is the person who emerges a mere copy, or is it a genuine continuation of your existence? Is the soul, if such a thing exists, bound to the original atoms or to the pattern they form? The gateway challenges the very idea of a permanent, unchanging self. It suggests that identity might be a pattern that can be transmitted, a story that can be retold in a different universe. This reshapes our understanding of time and cause. A wormhole could twist spacetime so severely that it connects two moments, allowing for travel into the past. This shatters our linear experience of cause and effect. If you could go back and prevent your own birth, you create a logical paradox that the universe seems to forbid. Perhaps, as some physicists suggest, the cosmos has a built-in consistency, a rule that prevents such contradictions from ever occurring. Your attempt to change the past would always fail in some subtle, unexpected way, preserving the timeline you remember. This idea has deep ethical echoes. If our universe was born from a white hole, a cosmic eruption from a parent reality, then we are not a singular creation. We are the offspring of another cosmos. This implies a causal chain, a lineage of universes, each giving birth to the next through its black holes. It transforms cosmology from a story of a single birth to an eternal cycle of creation. Such a narrative resonates with ancient creation myths and philosophical traditions that speak of cyclical time and multiple worlds. The gateway hypothesis forces a conversation between cutting-edge physics and humanity's oldest questions about our origins and our place in the grand scheme. It is not just a theory about tunnels in space, but a mirror held up to our deepest assumptions about existence, identity, and the nature of the cosmos itself. Humanity's oldest stories whisper of the same cosmic mystery. Long before telescopes, cultures across the globe described gateways to other realms. The ancient Greeks believed a dark cave at Cape Matapan was an entrance to the underworld, a literal passage to the land of the dead. In Buddhist tradition, the bardo is a transitional state between death and rebirth, a liminal space where consciousness journeys before its next form. These are not mere fantasies, but profound reflections of a deep-seated human yearning to know what lies beyond the veil of our immediate reality. The mythologist Joseph Campbell captured this universal tension when he said, "The cave you fear to enter holds the treasure you seek." That allure mixed with terror is exactly what we feel when we contemplate a black hole. We see this pattern everywhere. The Vikings spoke of Bifrost, a shimmering rainbow bridge connecting the world of humans to the realm of the gods. Aboriginal stories describe dreamtime pathways, sacred tracks crisscrossing the land that link the physical world to the spiritual creation era. Our modern fiction gives us the Stargate, a technological ring that creates a stable wormhole to distant planets. These narratives, ancient and new, all revolve around the same core idea, a doorway. cultures have often looked to the sky to find these portals. A sudden eclipse where the sun is swallowed by a mysterious shadow was seen by many as a temporary opening in the heavens. A brilliant comet streaking across the night sky was an omen, a messenger from another world. In this light, it is not so difficult to imagine how some indigenous cosmologies might interpret a black hole. That immense darkness in the cosmos could be seen as the eye of a creator, a window through which a spirit looks, or a sacred vortex where ancestors pass through. This rich historical context does more than just tell stories. It reveals that the desire to traverse dimensions is a timeless human impulse. Our ancestors gazed at the stars with the same fundamental curiosity that drives our astrophysicists today. They framed it in the language of myth and spirit, while we use the language of mathematics and relativity, but the underlying question is identical. What lies on the other side? This long, unbroken thread of imagination sets the stage for a staggering possibility. Perhaps our most advanced technology will one day catch up to our oldest dreams, turning the mythical gateway of our stories into the tangible reality of our future. Constructing a stable gateway would demand engineering on a cosmic scale. We are not talking about building a bridge of steel and concrete, but of weaving the fabric of spacetime itself, a task that would likely consume the entire energy output of a star. This is the realm of concepts like the Dyson sphere, a hypothetical megastructure that an advanced civilization might build to encircle a star and capture its total power. Physicist Freeman Dyson saw such engineering as a logical endpoint for technological growth, a signature we might one day detect in the cosmos. That unimaginable energy would be the bare minimum required for the first challenge, generating and concentrating enough exotic matter with negative energy to prop a wormhole open against its own gravity. The theoretical blueprint for such a structure is the Morris-Thorne wormhole, a solution that spells out the precise, bizarre properties this exotic matter must have. It would need to exert a tremendous outward pressure, creating a repulsive gravitational field strong enough to keep the tunnel's throat from pinching shut in an instant. This is not a material we could mine or create in a lab with our current understanding. It is a substance that defies the normal behavior of everything we know. The second monumental challenge is the stability of the passage itself. The quantum foam of spacetime is a seething, turbulent sea at the smallest scales. A wormhole would be a bubble in this foam, but one prone to violent, spontaneous collapse. Some theories suggest that quantum entanglement, that strange connection between particles across vast distances, could be harnessed to somehow lace the tunnel's structure, creating a coherent link that resists decay. The precision required is beyond comprehension. A single miscalculation and the gateway would implode, severing the connection in a catastrophic failure. Perhaps the most mind-bending application of a stable wormhole would be as a time machine. As explored by physicist Kip Thorne, if you could take one mouth of the wormhole and move it at a significant fraction of the speed of light, time dilation would take effect. Time would pass more slowly for the moving mouth relative to the stationary one. After a journey, if you brought the two mouths back together, you would not just have a bridge between 2 points in space, but a bridge between 2 different points in time. You could step into one mouth and emerge from the other in the past. The engineering for this is so far beyond our horizon it seems like magic, requiring the ability to move massive objects at relativistic speeds and manipulate spacetime geometry with flawless control. These are not technologies we can even dream of building today. They represent a frontier where the line between physics and engineering blurs entirely, a future that inspires our current research into quantum gravity and exotic materials. It forces us to confront a profound ethical dimension, a responsibility that comes with such ultimate power. To hold a gateway in your hands is to hold the keys to causality itself, to the timeline of history and the geography of the cosmos. The power to step between universes carries a responsibility as vast as the cosmos itself. If a black hole is a doorway, then we must ask who has the right to turn the handle and what rules should guide our first steps into the unknown. This is not merely a question for scientists, but for all of humanity. Consider the moment we discover a universe teeming with life, but life that has not yet developed technology. Do we observe from a distance or do we make contact? Our own history is stained with the tragedies of colonization, where advanced cultures destroyed vulnerable ones in the name of exploration. A real-world ethical framework, like philosopher Peter Singer's expansion of the moral circle, insists that our ethical obligations must extend to all beings capable of suffering, regardless of their planet or dimension of origin. The fictional Prime Directive from Star Trek provides a powerful template, a self-imposed law of non-interference to protect other cultures from our influence, no matter how well-intentioned. But the dangers run deeper than social disruption. Our very presence could be a form of dimensional pollution. We are made of atoms bound by the specific forces of our universe. What if we introduced a common Earth bacterium into a reality where it has no natural predators? It could become an unstoppable plague, wiping out entire biospheres. Conversely, what unknown hazards might we bring back? A microscopic pathogen from another dimension could be immune to all our medicines, or a particle with exotic properties could destabilize the very matter of our world. The governance of such gateways would become the most critical political challenge in human history. Who controls the passage? Would it be a single nation, a corporation, or a global coalition? The potential for exploitation, for claiming the resources of other universes, or for using a gateway as the ultimate military asset, could ignite conflicts that span realities. And then there is the personal cost. If you travel to a universe where time flows 1,000 times slower, a single day there might mean a decade has passed back on Earth. You could return to a world that has forgotten you, to loved ones who have grown old and passed away in your absence. Your journey would be a one-way ticket to the future, severing you from everything you once knew. These profound dilemmas reveal that the gateway hypothesis is far more than a physics problem. It is a mirror held up to our own maturity, our wisdom, and our capacity for foresight. It asks if we are ready, not just technologically, but ethically, to become a multi-dimensional species. Our stories have long prepared us for this moment, filling our minds with both the wonders and the warnings of stepping through the looking glass. The silver screen has transformed the black hole from a mathematical curiosity into a profound cultural icon. Films like Interstellar gave us Gargantua, a colossal, spinning black hole rendered with stunning scientific accuracy. Its glowing accretion disk, a whirlpool of superheated light, and the gravitational lensing that warped the starlight behind it were not just artistic choices. They were visualizations born from equations provided by physicist Kip Thorne, who collaborated closely with director Christopher Nolan. This commitment to realism did more than create a beautiful image. It made the abstract tangibility of warped spacetime accessible to millions. Suddenly, the public could see and feel the concepts physicists had been working with for decades, sparking a wave of fascination with the true nature of our cosmos. Other science fiction stories have taken this gateway concept in different, often darker directions. The film Event Horizon portrayed a black hole as a literal gateway to a hellish dimension, playing on the innate human fear of the unknown. The Monolith in 2001, A Space Odyssey, used a celestial gateway as a transformative tool for human evolution, suggesting a benevolent intelligence guiding us through these cosmic doors. And the Stargate franchise built an entire universe on the idea of stable, artificial wormholes, turning them into a practical tool for interstellar exploration. These portrayals always walk a delicate line between scientific plausibility and narrative drama. A completely accurate black hole would be a dark, silent, and relatively quick end for any protagonist, which does not always serve a story. So filmmakers take creative license, focusing on the most visually and thematically compelling aspects of the theory. This creative interpretation is not a flaw, but a feature. It creates a powerful feedback loop between science and culture. The concept of using a black hole for time travel, as dramatized in Interstellar, has been seriously debated in physics circles, pushing researchers to refine their models and consider the real-world implications. Public excitement generated by these films can translate into increased support for funding space telescopes and gravitational wave observatories, instruments that probe the very mysteries these stories depict. Our collective imagination, fed by science fiction, actively fuels the scientific curiosity that seeks to uncover the truth. The gateway hypothesis thrives in this space, a fertile ground where the dreams of storytellers and the calculations of scientists meet, each inspiring the other to look deeper into the cosmic dark. The equations of general relativity paint a smooth passage across the event horizon, but the quantum world might build a wall of fire there. This is the firewall paradox, a furious debate that erupted from the heart of the information problem. If information is not lost but must be preserved on the horizon, the delicate balance of spacetime predicted by Einstein shatters. To save quantum mechanics, you might need to incinerate anything that crosses the threshold with a searing barrier of high-energy particles. It is a stark choice between two fundamental pillars of physics. On one side of the scientific divide, you have the string theorists with their fuzzball proposal. They argue there is no smooth interior, no singularity, and therefore no firewall. The entire black hole from its horizon inward is a giant tangled ball of strings. There is no inside to traverse, only a dense, fuzzy surface. If this is true, then a black hole is not a gateway at all, but a final destination, a cosmic knot where matter is transformed but never escapes. Other interpretations of the holographic principle take this further. What if the black hole we see is not a physical object in our space, but a holographic projection from a distant, two-dimensional surface? The event horizon would be a cosmic screen, and the three-dimensional darkness we observe is merely an illusion. You could no more walk through it than you could step into a movie. These competing models clash in conference halls where whiteboards are filled with the elegant script of mathematics. The late Stephen Hawking himself shifted his ground in this debate. After decades of insisting information was lost, he proposed black holes might have soft hair, subtle quantum imprints on their horizon that could store data without a violent firewall. This was a significant step, a nod toward the possibility that information could be preserved, making the gateway hypothesis slightly more plausible. Yet the core conflict remains unresolved, a testament to the fact that we are still grappling with the true nature of reality. This vibrant, often contentious debate is not a sign of failure, but the very engine of scientific discovery. It forces us to question our assumptions, to refine our models, and to look for the crucial evidence that will tip the scales. The journey to understand black holes is a journey to the edge of known physics, where every answer births a dozen new, more profound questions. The idea of a cosmic shredder offers a stark and sobering alternative to the gateway. Some of the most brilliant minds in physics argue that a black hole is precisely what its classical description suggests, a final and irreversible endpoint. This perspective is crystallized in the no-hair theorem, a principle suggesting that a black hole can be completely described by only three properties: its mass, its electric charge, and its spin. Everything else, every intricate detail about the matter that fell in, is permanently erased. All the information that made up a star, a planet, or a person is utterly destroyed, leaving behind a perfectly smooth, featureless void. This is the ultimate cosmic erase button. The legendary physicist Roger Penrose, who first mapped the mathematics of singularities, champions a view where information loss is not just possible but essential. His conformal cyclic cosmology paints a breathtaking picture of an eternal universe, where the distant future of one cosmic era becomes the Big Bang of the next. In this grand cycle, black holes play a vital role. They evaporate away through Hawking radiation, and in doing so, all the information they consumed is permanently lost. This very loss of information is what resets the cosmic clock, wiping the slate clean for a new universe to be born from the ashes of the old. It is a cycle of creation, but one that offers no passage for travelers, only a total and final dissolution. This view is mathematically consistent and elegantly sidesteps the need for exotic gateways. It strictly adheres to the second law of thermodynamics, which dictates that disorder or entropy always increases. If information could escape a black hole unscathed, it might violate this fundamental law, allowing for a decrease in universal disorder that physics cannot easily explain. Resolving the information paradox then requires a different kind of solution. One possibility is the existence of Planck-scale remnants, incredibly dense, tiny objects left over after a black hole evaporates. These remnants would contain all the information that fell in, but they would be stable, eternal vaults, locking the data away forever in a form we could never access. This perspective forces a crucial counterbalance to the thrilling gateway narrative. It grounds us in the possibility that the universe's most terrifying objects are exactly that, final graves where the story of matter truly ends. The fiery debate between these two visions, the gateway and the shredder, is not just philosophical. It pushes us toward the only arbiter that matters, the experimental frontier, where the universe itself will reveal its ultimate secrets. The ripples from two colliding black holes carry secrets in their wake. When LISA, the Laser Interferometer Space Antenna, begins listening to the cosmos in the coming decades, it will catch these gravitational whispers with unprecedented clarity. This space-based observatory, a trio of satellites flying in a perfect triangle millions of kilometers apart, will detect the faintest tremors in spacetime. Scientists like Vita Cardoso suggest that the final moments of a black hole merger could produce more than just a single crash. If the event horizon is not a perfect, smooth boundary but the entrance to a deeper structure, the collision might create echoes. Think of spacetime ringing like a bell, with the initial gravitational wave signal followed by faint, repeating reverberations from the quantum structure of the horizon itself. These echoes would be the first direct evidence that there is something beyond the veil, a complex interior that could be the throat of a wormhole. We can also stare directly into the darkness for clues. The Event Horizon Telescope's first image of a black hole's shadow was a monumental achievement, but future versions of this telescope, with more stations across the globe and even in space, will capture that shadow in exquisite detail. A normal black hole's shadow should appear as a near-perfect circle, a dark disk framed by a bright ring of light, but a wormhole's mouth might be different. Its shadow could be distorted, perhaps showing a double image or a subtle, telltale asymmetry caused by the exotic matter holding it open. It would be a fingerprint of a gateway visible from Earth. The search extends to the most energetic particles in the universe. Immense neutrino telescopes buried deep in Antarctic ice and sprawling cosmic ray detectors on high mountain plateaus are constantly scanning the skies. If a black hole is connected to another universe, what prevents some material or energy from that other side from leaking through? We might detect a burst of ultra-high energy neutrinos that cannot be explained by any known astrophysical source, or a cosmic ray particle with properties that defy the standard model of physics. These anomalous particles could be visitors from another reality, ejected from the white hole exit of the cosmic tunnel. Even the oldest light in the universe, the cosmic microwave background, could hold a clue. This faint afterglow of the Big Bang is a snapshot of the infant cosmos. If our universe itself was born from a white hole in a parent cosmos, the immense energy of that eruption might have left a unique pattern, a subtle bruise or a directional asymmetry in this primordial radiation. Finding such an imprint would be evidence that we are living inside the result of a gateway event. Perhaps the most revolutionary tool for testing these ideas is not a telescope, but a quantum computer. Simulating the chaotic quantum environment near a black hole singularity is impossible for classical computers, but a sufficiently advanced quantum computer, which operates on the same probabilistic principles, could model the behavior of information and matter falling into a black hole. It could run digital experiments to see if information is truly scrambled and lost, or if it is preserved and transmitted, as the gateway theory requires. This virtual laboratory could predict the specific signatures we should look for in real-world observations, guiding our search with digital precision. Each of these experimental paths transforms a beautiful philosophical idea into a hard, empirical question. They are driving a new era of technological innovation, pushing us to build more sensitive ears to listen to space-time and sharper eyes to peer into the abyss. The answers we find will not just tell us about black holes, they will define the trajectory of our civilization, revealing whether we are forever confined to our own cosmic shore or stand at the beginning of an infinite journey. Our universe is slowly fading. Trillions of years from now, stars will have burned out, galaxies will have drifted apart into an ever-cooling darkness, and the cosmic background radiation will have dwindled to a faint, cold whisper. In this final epoch, black holes will become the last islands of concentrated energy and structure in an otherwise silent and empty expanse. For any civilization that survives to witness this era, these gravitational giants may offer the only hope for continued existence. They could become the ultimate lifeboats. Picture a society huddled around the last supermassive black hole, a final flicker of warmth and light in an ocean of eternal night. Their entire survival might depend on harnessing its power or, more profoundly, on finding a way to step through it. The physicist Freeman Dyson contemplated such open-ended evolution, where intelligence would have to adapt to an ever-changing cosmos on scales we can barely conceive. Using a black hole as a gateway would be the ultimate adaptation, a desperate leap from a dying universe into a new one still vibrant with energy and possibility. This is not a retreat but a migration on the grandest possible scale. The process itself could be a natural cosmic cycle. As black holes evaporate over incomprehensible eons through Hawking radiation, their final moments are not a silent fade to black. The last burst of energy could be a creative act. Some quantum gravity models suggest that the death of a black hole might trigger the birth of a new universe in a vast multiverse, a cosmic phoenix rising from its own ashes. In this view, every black hole is a potential seed for a new reality, and an advanced civilization might learn to cultivate them. This leads to the staggering concept of black hole farming. A future society could build immense structures to capture the Hawking radiation from a collection of small, engineered black holes, using them as power plants to sustain their civilization for eons. But the ultimate goal would be gateway engineering. With that power, they could attempt to stabilize a large, natural black hole, reinforcing its structure with generated exotic matter to transform it from a potential death trap into a guaranteed passage. If the multiverse is real, then these gateways are not just theoretical curiosities, but natural migration routes written into the fabric of spacetime. When our universe becomes too cold and dilute to support any form of complex processes, a black hole would be the only door leading out. This long-term perspective transforms our understanding of their role. They are not just destructive forces or astronomical curiosities, but essential components in the universe's large-scale structure, potentially serving as recycling centers for reality itself and the final refuge for intelligence against the dying of the light. A supermassive black hole anchors nearly every galaxy we see. These are not passive monsters lurking in the dark, but active, dynamic engines that shape the very cities of stars they inhabit. Astronomer Andrea Ghez, who won a Nobel Prize for her work on our own galaxy's heart, Sagittarius A star, put it simply, black holes are a key ingredient in the evolution of galaxies. Their influence is profound and twofold, a process astronomers call feedback. In a violent, explosive mode, a feeding black hole can blast out colossal jets of energy and wind, blowing away the gas clouds that would have formed new stars, effectively shutting down a galaxy's growth. In a quieter, more gentle mode, the energy it releases can heat surrounding gas, preventing it from cooling and collapsing into stars, regulating the pace of creation. This intricate dance between destruction and regulation suggests a deep cosmic connection. We see a stunning correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, as if the invisible heart of the system knows the size of its cosmic body. Now layer the gateway hypothesis onto this established picture. If a black hole is not just an engine but a tunnel, then this feedback loop takes on an entirely new dimension. The immense energy pouring out could be more than just recycled cosmic material. It might be the exhaust from another reality. Matter falling into the black hole on one side of the gateway could be funneled through, and its energy might be expressed as a jet or wind erupting from the connected white hole in another dimension. This could mean that the growth and evolution of galaxies are not isolated events, but are subtly influenced by processes occurring in other universes. This perspective even offers a radical new way to view the universe's greatest mysteries, dark matter and dark energy. What if dark matter, the invisible glue holding galaxies together, is not a particle at all, but the gravitational shadow of matter in a parallel reality, its pull leaking through these cosmic gateways? And what if the repulsive force of dark energy accelerating the universe's expansion is the gentle pressure from this constant, low-level exchange between dimensions? If black holes are leaking even a tiny amount of energy or information into other realms, it could slightly alter the energy balance of our own cosmos, affecting the expansion rate over billions of years. This large-scale view integrates black holes into the very fabric of cosmic architecture. They become more than just objects, they are potential nodes in an interdimensional network, the fundamental crossroads where the fate of galaxies is woven together with the structure of the multiverse. To truly grasp how such a connection could work, we must follow the trail down to the most basic level of reality, to the nature of information itself. Quantum entanglement weaves an invisible thread between particles, binding their fates across any distance. This strange connection could be the very mechanism that stitches a gateway through a black hole's heart. Picture two entangled particles, a linked pair, falling into the abyss. Their unbreakable quantum bond might not be severed by the event horizon. Instead, it could theoretically stretch and twist, carving a stable bridge through the chaotic singularity. This is the core of a revolutionary idea known as the ER=EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind. The ER refers to the Einstein-Rosen bridge, the wormhole, while EPR represents Einstein-Podolsky-Rosen, the famous paper on entanglement. Their bold proposal is that these two seemingly different concepts are one and the same. Entanglement does not just describe a connection, it physically is a connection, a microscopic wormhole woven into the fabric of spacetime itself. This means that if two black holes become entangled, perhaps from being born from the same stellar collapse or through some later interaction, they would not be separate objects. They would be linked by a wormhole, a tunnel through the higher dimensions predicted by string theory. Their event horizons would be quantumly married, creating a single, complex structure. This provides a stunning solution to the puzzle of how information escapes a black hole. The information is not traveling through space, it is simply manifesting on the other side of the quantum link, an instantaneous correlation that respects the laws of physics because no matter or energy is actually moving faster than light. This idea fits perfectly with the holographic principle. The entanglement of quantum degrees of freedom on the two-dimensional surface of the event horizon does not just store information, it actively builds the geometry of the black hole's interior. The more entangled the particles on the surface are, the more connected the interior becomes, potentially forging the wormhole throat itself. We are now testing these profound ideas not with giant telescopes but with quantum computers. Researchers are creating tiny simulated black holes in these advanced machines, entangling their quantum bits and watching how information behaves. They are looking for signatures of wormhole formation, for evidence that entanglement truly can birth a gateway. This quantum perspective completely transforms our understanding. A gateway is not necessarily a tunnel you fly through in a spaceship. It might be a fundamental property of deeply entangled information, a place where the line between a data stream and a physical passage dissolves entirely. This forces us to confront the very limits of our theories, suggesting that spacetime itself may be a secondary structure, emerging from a deeper, more fundamental network of quantum connections. General relativity paints a majestic portrait of curved spacetime, a cosmic canvas where gravity is the artist. Yet this masterpiece frays at the edges when we peer into the heart of a black hole. The equations point to a singularity, a place of infinite density where the fabric of reality itself tears apart. This is not a sign that the theory is wrong, but that it is incomplete. It is like a beautiful, detailed map that suddenly shows the edge of the world with the warning, "Here be dragons." To cross that threshold, we need a new kind of map, one that charts the quantum dragons. The singularity is that frayed end of a rope where our classical understanding of gravity unravels into nonsense. A complete theory of quantum gravity would be the hand that weaves those frayed threads into a new, coherent structure, perhaps the very fabric of a gateway. The challenge in creating this theory is a clash of cosmic titans. General relativity is deterministic and smooth, describing gravity as the elegant curvature of a continuous space-time landscape. Quantum mechanics, in stark contrast, is probabilistic and granular, painting a world of uncertainty and discrete packets of energy. Forcing them together is like trying to mix oil and water. When physicists attempt to quantize gravity using the same tools that worked for other forces, the mathematics explodes with infinities that cannot be tamed, a problem known as non-renormalizability. This fundamental conflict is why we need a radically new approach. Different paths lead into this unknown. String theory proposes that the fundamental ingredients of reality are tiny, vibrating strings, and that gravity emerges from their harmonious interactions in extra dimensions. Loop quantum gravity, pioneered by Carlo Rovelli, takes a different route. It suggests that spacetime itself is not smooth and continuous, but woven from a fabric of tiny, finite loops. Think of the universe not as a perfectly smooth sheet of glass, but as an incredibly fine piece of cloth with 1 trillion threads per square inch. In this view, there can be no true singularity, no point of infinite density, because you simply run out of fabric. The weave becomes so tight it can tighten no further, and then it may rebound. This leads to a breathtaking possibility for black holes. Instead of ending in a catastrophic singularity, a black hole in loop quantum gravity could reach a maximum density, and then quantum effects would cause it to bounce, transforming into a white hole. This would create a natural, singularity-free gateway, where anything that falls into the black hole is eventually expelled from the white hole into a new region of spacetime. The implications are profound. If loop quantum gravity is correct, then gateways might not be rare anomalies, but a fundamental part of a black hole's life cycle. This acknowledgement of general relativity's limits does more than refine our equations. It humbles our speculation. It reminds us that the gateway hypothesis lives or dies on the outcome of this grand quest for a unified theory. The reality we perceive is limited by the tools we have to observe it. This journey to the edge of physics inevitably leads us to a final, deeply personal frontier: the role of the observer in the cosmos. Our consciousness is a phenomenon sculpted by the three-dimensional world we inhabit. Every thought, every sensation, is filtered through a brain that evolved to navigate length, width, and height. But what happens when that framework is radically altered by a journey through a black hole gateway? The very act of perception could break down entirely. Philosopher David Chalmers framed the hard problem of consciousness, questioning why the intricate electrical and chemical dance in our brains should produce a rich inner life, a subjective experience of the color red or the feeling of awe. This mystery becomes exponentially stranger when we consider higher dimensions. If you were to pass through a gateway into a universe with 4 spatial dimensions, your 3-dimensional senses would be utterly unequipped to process it. You might not see a new world, but instead experience a chaotic flood of incomprehensible data, a sensory overload that could shatter your sense of self. This leads to a profound philosophical hypothesis: panpsychism. This is the idea that consciousness is not a rare product of complex brains, but a fundamental property of the universe, as basic as mass or charge. If panpsychism is true, then consciousness might permeate all dimensions. Your sense of self would not be tied solely to your physical brain, but to a deeper, more universal substrate. Passing through a gateway would not erase you. It would translate your conscious experience into a new dimensional context. You might perceive reality in a way we cannot currently fathom, experiencing time as a physical landscape or seeing the inside of every object simultaneously. To navigate such a reality, our ordinary state of mind would be useless. We might require advanced technology to act as a perceptual filter, or we would need to induce profoundly altered states of consciousness, perhaps through meditation or neurotechnology, to even begin to comprehend our surroundings. Some speculative theories go further, suggesting that black holes are not just spatial portals, but gateways to different states of awareness itself. The immense gravitational and quantum forces at the event horizon could trigger a shift in consciousness, unlocking perceptual capacities that are latent within the mind. This intersection of physics and philosophy reveals that the ultimate challenge of gateway travel may not be engineering, but introspection. the journey would demand that we evolve not just our technology, but our very minds, pushing the boundaries of what it means to be aware and to be a self in a cosmos of limitless dimensions. These cosmic laboratories offer more than just a potential passage. They are powerful tools for discovery, pushing the very limits of human knowledge. Imagine a future where we deploy a fleet of robotic probes, no larger than your hand, on a one-way mission to the edge of a black hole. These tiny craft, built with technology like the Breakthrough Starshot initiative envisions for interstellar travel, could be our eyes and ears at the precipice. They would brave the extreme environment to measure space-time curvature with unimaginable precision and hunt for the subtle signatures of quantum effects near the event horizon, data we can never collect from the safety of our own solar system. This is not science fiction, but a logical extension of our current drive to explore. We are already using black holes as natural experiments. For decades, astronomers have meticulously tracked the orbits of stars whipping around our galaxy's own supermassive black hole, Sagittarius A star. The precise paths these stars take are a perfect test of Einstein's general relativity under the most intense gravity imaginable, and so far, his predictions hold stunningly true. We also search for flashes of high-energy light that could signal the annihilation of dark matter particles drawn into the black hole's grip, potentially revealing the nature of this invisible cosmic component. Their utility extends even further. A black hole's immense gravity bends light like a giant lens, magnifying objects far behind it. This gravitational lensing acts as a natural telescope, allowing us to peer at galaxies so distant and faint they would otherwise be invisible. And for a future civilization, the very spin of a black hole could become an energy source. The Penrose process, once a theoretical curiosity, outlines how we could literally extract energy from a rotating black hole's ergosphere, tapping the power of spacetime itself. Even the gateway hypothesis has practical experimental value. If a black hole is connected to another realm, the faint Hawking radiation it emits might not be entirely random. Its spectrum, the specific energy signature of this glow, could be imprinted with subtle anomalies, a scrambled code leaking information about the physics of the connected universe. This perspective transforms our view completely. Whether they are traversable gateways or not, black holes are undeniable engines of discovery. They force us to build better telescopes, to dream of ambitious missions, and to refine our most fundamental theories. The drive to understand them is already propelling our technology and imagination forward, proving that the greatest value of these dark giants may lie not in where they lead, but in how they make us reach. The true nature of the singularity remains one of physics' greatest enigmas. Is it a point of infinite density, a gateway to another realm, or something else entirely that our current mathematics cannot describe? This mystery is deeply intertwined with the question of information. Does it escape a black hole, scrambled into Hawking radiation, or is it lost forever, violating a fundamental quantum law? The resolution of this paradox will determine if black holes are cosmic shredders or complex transformers. And what of white holes? Their mathematical elegance is undeniable, but their physical reality remains unproven, leaving us to wonder if they are the other end of the tunnel or merely a beautiful illusion. These questions are not isolated. They connect to grander cosmic theories, like physicist Lee Smollen's idea of cosmic natural selection. This provocative concept suggests that universes themselves evolve, with black holes acting as reproductive organs. Each black hole could spawn a new universe with slightly altered physical constants. The universes that produce the most black holes would, in turn, create the most offspring, leading to a cosmic landscape fine-tuned for black hole formation. But how would this process actually work? the mechanism remains hidden within the unknown laws of quantum gravity. We are also still grappling with the origin of black hole entropy. Why does the event horizon surface area correspond to such an immense amount of hidden information? And what are the microscopic quantum states that account for it? Solving this could reveal if the horizon is a chaotic mess or a perfectly ordered data storage system. Then there is the persistent firewall paradox. Does a wall of searing energy incinerate anything at the event horizon? Or is the passage smooth as Einstein predicted? The answer forces a choice between the pillars of quantum mechanics and general relativity, a choice we are not yet equipped to make. The feasibility of stable wormholes hinges on these answers. Could dark energy, the mysterious force accelerating the universe's expansion, play a role in propping open a gateway? Its repulsive gravity might be the natural counterbalance to a wormhole's collapse, a cosmic constant acting as permanent scaffolding. As we push toward a theory of quantum gravity, we might discover entirely new types of spacetime structures, geometries beyond our current imagination that make gateways not just possible but commonplace. All these theoretical struggles lead to a very practical observational question. If black holes are gateways, why does our universe seem to be a one-way street? We see matter falling in, but we have never observed a sudden, inexplicable influx of matter or energy from another reality pouring out. Is our cosmos simply on the receiving end of a vast cosmic network? Or are the exits so well hidden we have not yet learned to see them? These are the open questions that fuel all-night sessions in physics departments and drive the design of next-generation telescopes. They remind us that the gateway hypothesis is a single piece in a much larger puzzle, a puzzle whose final image will redefine our place in the cosmos. This sense of unfinished inquiry is not a failure, but the very engine of discovery, a constant reminder that the greatest adventures in understanding still lie ahead. Our journey through the cosmic doorway brings us to a final, humbling reflection. We have ventured from the silent threshold of the event horizon to the very edges of theoretical physics, exploring a possibility that reshapes our place in the cosmos. The idea that black holes could be gateways is more than a scientific hypothesis. It is a narrative that redefines the universe from a collection of isolated objects into a network of potential connections. We have seen how the mathematics of rotating black holes and the bizarre properties of exotic matter could forge stable tunnels through space-time. We have traced the thread from quantum entanglement, where information itself might weave the fabric of a wormhole, to the grand vision of a multiverse, where every black hole might be a creator of new realities. Yet this incredible potential is balanced by immense challenges, from the technological feat of engineering such a passage to the profound ethical responsibility of stepping through it. These concepts do more than spark scientific curiosity. They invite a deeper appreciation for the universe's fundamental mysteries. They remind us that our quest for knowledge is a journey without a final destination, driven by the enduring truth in Carl Sagan's words, that somewhere, something incredible is waiting to be known. So I leave you with a question not just of science but of imagination. If you stood before such a gateway, what forgotten corner of reality would you dare to explore? Share your thoughts in the comments below. If these space mysteries captivate you, subscribe for more journeys to the edge of understanding. Keep looking up, for the universe is not a cold, dark void, but a cosmos full of doors, each one waiting for a curious mind to turn the handle.